Welcome. In this lecture, we are going to do governing equations and conservation laws, by which I mean mass conservation, momentum conservation, and energy conservation. So, conservation laws and other forms of governing equations play very important role in any fluid dynamics problem, and in environmental fluid mechanics, they are all equally important because generally we deal with very complicated systems and it's very difficult to get direct results, so we need to deal with or we need to use these complex governing equations, and based on that, by applying necessary boundary conditions and initial conditions, we get the required results. So before we go and solve for different type of flows, we need to quickly revise the conservation laws and other forms of governing equations, which we are going to do in today's lecture. So the very first with material derivative, which is something you might have studied before. So material derivative is obviously it's not really a conservation law. It's just a mathematical formulation. But this is very useful when we define conservation laws because this helps us in shortening long equations. Okay, so this is generally written as capital D phi by capital DT is equal to d phi by dt plus u d phi by dx plus v d phi by dy plus w d phi by dz. Okay, where we are assuming x, y, z are the coordinate system, and u, v, w are the velocities in x, y, z directions. Okay, and t here is time. And another thing that we see here is phi, and phi is some scalar or vector quantity. Okay, so this equation that we have can be used for any scalar or vector quantity, which also includes, let's say, velocity or maybe density, etc. Okay, so if we put velocity in case of phi, then this equation becomes force equation where or acceleration equation where du by dt actually gives you the acceleration, right? So in this particular equation, we see different terms, which let's discuss one by one. So this equation is this particular term, the first term is known as the total or material derivative. This term is the local or temporal derivative, and these three terms together are advective or convective derivatives, right? So what exactly it means? So we have total derivative that is the sum of local and advective derivative. So when you have a fluid problem or mixing problem where your particular parameter is changing both in space and time, and you want to combine the effects of both or couple the effects of both time and space, then you need to use this particular formula. And that is how you find the total derivative or total change. So when we say derivative, we actually mean the total change in that particular property, right? And let's say if you use if phi is equal to u, that is velocity, then d phi by dt basically becomes du by dt. That becomes your a total. So total acceleration, right? And a total can be given as du by dt plus u du by dx plus v du by dy plus w du by dz. So basically a total is equal to a with respect to time plus a with respect to x. So here we obviously have the this is little confusing. So we can actually call the total acceleration is equal to local acceleration plus advective acceleration. Okay, so when we replace phi with velocity in case of material derivative, that actually gives us the acceleration, because what is the rate of change of velocity? That is basically acceleration. And in this case, now your velocity is changing both in time and space, and that is how you get the local acceleration as well as advective acceleration, and you sum them up, that gives you total acceleration. Okay, so that is the material derivative, which is quite useful in solving different type of problems. Now let's do several conservation laws, and we will do mass conservation, momentum conservation, and energy conservation. Okay, where mass conservation is basically mass balance, momentum conservation is force balance, and this is of course energy balance. Okay, so these are three different type of conservation equations we apply in case of a fluid or mixing problem. So let's start with mass conservation. So mass conservation and also other forms of conservation equations can be written in two different forms. So first is called bulk form, which is also generally called integral form, which actually is written as m dot in minus m dot out is simply equal to dm by dt for a system. Okay, for a system where this is mass influx into the system, this is mass outflux from the system, and this one is the mass accumulation term, right? So what exactly mass accumulation term mean? So if you have a control volume where you have some mass coming in and mass going out, but let's assume that within that control volume, if there is mass generation, okay, or there is loss of mass, so that loss of mass or extra mass that is getting generated must be equal to the mass that is coming in minus mass that is going out. Okay, and that is very simple. Very simply, the conservation, mass conservation in its bulk form, in integral form, right? And then this is quite straightforward. But then we also have the second one that is called the differential form, which popularly known as the continuity equation. Okay, so continuity equation for a mass conservation is written as d rho by dt plus u d by dx rho u plus d by dy rho v plus d by dz rho w is equal to 0. Okay, where rho is the fluid density. Okay, and once again, u, v, w are the velocities and x, y, z are the coordinate system. Right? So this is the mass conservation. So basically, all your velocities in all three directions are not independent of each other. They actually depend on each other because they have to conserve mass, right? And if the flow is incompressible, okay, what does it mean? Rho is constant, right? Rho is not changing. If the flow is incompressible, in that case, your mass conservation equation looks like this: du by dx plus dv by dy plus dw by dz is equal to 0. Okay, so this is the form of mass conservation or continuity equation in incompressible situation. Okay, and this is another common form of mass conservation that is used because many times or most of the time we consider the flow to be incompressible. Okay, so this is the continuity equation for incompressible flow. Okay, so now let's move to the next one. We already done mass conservation. Now we'll talk about momentum conservation. And in case of momentum conservation, we will directly go to the differential form. Which is popularly known as the Navier-Stokes equation. Okay, so now in case of momentum equation, we don't have just one equation, but we have three different equations. Why? Because momentum is a vector quantity, whereas mass is a scalar quantity, right? So you have forces in all three different directions, and whenever you do a force balance, you have to do individual force balance for x, y, and z directions, and that is why Navier-Stokes equations have are written in three different directions. So in x, it is written as capital du by dt is equal to minus dp by dx plus mu d square u by dy square plus d square v by dy square plus d square w by dz square plus rho gx. Okay, and then in case of y direction, the same can be written as dv by dt is equal to minus dp by dy plus mu. Sorry, there is a mistake here. This is x. So d square v by dx square plus d square v by dy square plus d square v by dz square plus rho g y. Okay, and then in z direction, the same can be written as dw by dt is equal to minus dp by dz plus mu d square w by dx square plus d square w by dy square plus d square w by dz square plus rho g z. Okay, so these are three different Navier-Stokes equations in each written in each direction in x, y, and z, because we have to do force balance or momentum balance in each direction individually. Okay, and the capital D by dt that you see here is actually the material derivative, something that we already did in the just a few minutes back. And G here is the gravity, which has component Gx, Gy, Gz is the gravity term. Okay, if we assume Z is vertical, which means this is your Z axis and then you have your X and Y. In that case, you have G in this direction, in downward direction, and Z is upward direction. In that case, your Gx is 0, Gy is 0, and Gz is equal to minus G. Okay, so components of G in X and Y directions are 0, and it has component only in Z direction, and that too has the negative value. And that is why G is 0, 0, minus G for vertical Z direction. Okay, so in this case, we can rewrite this equation with Gx and Gy to be equal to 0 and Z to be minus G. Okay, so let me expand the Navier-Stokes equation in Z. In Z direction, that is the vertical direction, we can write this as rho dw by dt plus u dw by dx plus v dw by dy plus w dw by dz is equal to minus dw by dz plus mu d square w by dx square plus d square w by dy square plus d square w by dz square minus rho g. Okay, so this is the Navier-Stokes equation in z direction, which is the vertical direction. And now if you want to write in x and y direction, your g component in these equations will be 0 and in other terms will remain same. So now coming back to this equation, now we see this is the expanded equation and we see several different terms, right? So in this case, let's see what all these different terms mean one by one. And probably we can take this to the next page. Okay, so in this case, the first term here is the local acceleration term, and these are the advective acceleration terms. Okay, there is a mistake again here. This has to be P. Okay, this is the pressure force term. These are the viscous force term. And what you see here is the body force or gravity force. Okay, so what you see in rho g is actually the body force term, but for most of our cases, we don't consider any other body force. We only consider the gravity as the body force, and that's why we are not worried about other forces. And in these cases, these two terms together are known as the inertia force terms. Okay, so what do you see here is the left hand side is the inertia force together for the local inertia force as well as advective inertia force. In the total inertia force in a fluid body or fluid motion must be equal to the resultant force that comes from the pressure force, viscous force, and the body force or the gravity force. Okay, so this is the Navier-Stokes equation in z direction, and obviously we have similar equations in x and y direction. Okay, now we will move to the energy equation. So energy equation is written in terms of temperature because we are trying to conserve heat energy here, and that is written as, again we can write that in full derivative form like this: capital D by dt q by rho Cp plus k by rho Cp, and this is d square t by dx square plus d square t by dy square plus d square t by dz square, which can be expanded further, and that becomes dt plus u dt by dx plus v dt by dy plus w dt by dz is equal to q by rho Cp plus k by rho Cp is d square t by dx square plus d square t by dy square plus d square t by dz square. Right, and once again here we have the local change in temperature, advective change in temperature, and then we have the source or sink term, and then we have the diffusion term. Okay, so local temperature variation, these are the advective variation. This is the heat generation or loss term. Okay, and this is the heat diffusion term. Okay, so what again you see here is you have heat generation or loss term. So if there is, for instance, there is a coil which is generating heat, that can be considered as heat generation term. And then heat diffusion is because of the thermal conductivity, right? Heat is transferring through conduction. And then if you remember, we also talked about the advective term, right? The flow is moving, so there is convection happening because of the fluid motion, because of the fluid parcels, right? And that comes in the left hand side. Okay, so in this case, Q is the heat generation or loss. Okay, rho is the fluid density, Cp is the heat capacity. Okay, and K is the thermal conductivity. Okay, and usually K by rho Cp is written as alpha, which is known as thermal diffusivity. Okay, so thermal diffusivity is similar to kinematic viscosity for fluid motion. Thermal diffusivity is for heat transfer. Okay, and of course the T term here, capital T, is the temperature. Okay, so this is the equation used for writing energy balance. Okay, and we have just one equation for energy balance. Why? Because energy is a scalar quantity. So now there is an equivalent equation for energy conservation, and that is called solute balance. Solute balance equation, also known as the advection diffusion equation. This is equivalent to the energy equation for solute concentration. Okay, so here we don't consider temperature, but we consider solute concentration. And this equation is written as dc by dt plus u dc by dx plus v dc by dy plus w dc by dz is equal to d square. Okay, so being consistent with the previous equation, we need to write the m dot term here first, plus d square c by dx square, d square c by dy square, d square c by dz square. Okay, so this is the solute transport equation, where C here is the solute concentration and M here is the mass generation or loss term, which also known as the source or sink term. Okay, so if you have some extra mass coming into the system or mass is getting lost during the flow, so you consider m dot there, and then c is the concentration, and t here is the diffusion or dispersion coefficient. Okay, and this is the same equation that we already did in previous lecture for a simplified condition. There we assume that C is not changing with time, and also there was no mass generation or loss term, and also we considered that velocity was just in one direction and diffusion was happening in another direction. So we tried to okay, so there was time term, but other terms were not there. So it was a highly simplified equation. Okay, but this is a complete solute transport equation where we have the unsteady term, we have advective term, we have mass generation or loss term, and also we have source and we have the diffusion term as well, right? And what exactly it means again? So this part is the advective term, and this part is the diffusive term, right? So in fact, this part can be called the advective term because that is related to the velocity, and then dc by dt can be called either local change in concentration or accumulation term. Okay, so this is another equation that we might need when we solve for the mixing problem in this course. Okay, now moving to the next equation, and that is the Bernoulli equation. So far we have done mass balance, force balance, energy balance, where in energy we did either heat or solute mass, right? So we have one equation for mass balance, three equations for force balance or momentum conservation, in one equation for energy balance. And in case of energy balance, either we use one equation for heat balance or one equation for solute mass balance. Okay, so these are different equations we have when we are trying to solve a complete fluid dynamics problem, or in case of environmental fluid mechanics, where we can also use this solute mass balance in addition to the heat balance. Okay. Now we will quickly revise the Bernoulli equation. Bernoulli equation is another fundamental equation in fluid mechanics, which I assume you all have studied already, and that is why we will quickly revise it rather than going into the full details of it. So this is written as P by rho g plus U square by 2g plus Z is equal to constant. Okay, where P is the pressure, rho is the density, U is the velocity, G is the gravity term, and Z is the elevation. Right? So here, what you have here is, this is known as the pressure head or flow energy. This one is velocity, head, or kinetic energy. And the third one is elevation, head, or potential energy. Okay, so these are three different terms that we have, or three different parts of energy we have during fluid flow. So it can have kinetic energy, which is in form of velocity. So if it has higher velocity, it means it has higher kinetic energy, or we call it velocity head. If it has higher elevation, going from higher elevation to lower elevation, then we call it potential energy, because this is related to the gravity. And then we have pressure head, or that is also known as the flow energy, because not necessarily fluid is flowing always at the atmospheric pressure. It might have higher pressure than the atmospheric pressure, so there might be pressure variation when you go from one point to another, and that is why there is pressure head or flow energy involved in the system. And now when you add these three things together, for given set of conditions, these three some of these three quantities are always constant. Okay, so this is, as I said, is for given set of conditions, not just in any condition, but for those given conditions, this can be considered, the sum of this can be considered constant at any point in the flow. So what conditions are used? uh, Bernoulli equation. Assumptions. First is incompressible flow, such that your rho is constant or density is constant. Second condition is inviscid flow. So when we say inviscid, we assume mu is almost equal to 0. So effects of viscosity is 0. Viscous effects are equal to 0. And then a steady flow, which means that anything that is there inside the time derivative is equal to 0. Okay, which involves, let's say, d rho by dt is equal to 0, or du by dt is equal to 0, etc. And then flow is irrotational, and that's why this is conserved everywhere or constant everywhere. And then we also assume constant temperature. Okay, so these are some of the conditions under which this form of Bernoulli equation uh, is conserved. But if you change the condition, you can still write Bernoulli equation. It might have different forms, and it might be conserved in different conditions, all these parameters that we have written. Okay, but for the given set of conditions, we can write this particular form where pressure head, velocity head, and elevation head are constant anywhere in the flow. Okay, and what exactly is Bernoulli equation? So we have already seen mass balance, force balance, and energy balance. So Bernoulli equation is form of energy balance, but for a given set of conditions. In a normal fluid flow, you cannot consider this equation to be balancing energy, because this works only when certain conditions are satisfied. Okay, and now finally we will move to our last equation, which we might need for solving uh, some of our fluid problems, and that is the equation of state. And this is another equation that you have studied previously in your physics course, but we will quickly revise it. So we will write two different equations of states. So one is in terms of temperature and other one in terms of concentration. So here is 1 minus gamma T minus T naught, where T naught is the reference temperature, rho naught is the density at T naught, and gamma is the thermal expansion coefficient. Okay, and then another form of equation of state is written in terms of concentration. So that is 1 plus beta C minus C naught. So in this case now C naught is the reference concentration rho naught is the density at C equal to C naught. Beta is known as the solute contraction coefficient. Okay, and here obviously rho is the density is and C is the solute concentration. Whereas in this case, obviously rho is still the same density and T is the fluid temperature. Okay, so these are two different equations we have. One is relating density with the temperature and other one is relating density with the concentration. So to understand this, we imagine if we heat a fluid, it creates buoyancy, it becomes lighter and tries to uh, rise up. And that happens because there is expansion of fluid particles, so density becomes smaller. Whereas in case of concentration, if you add more and more solute, so basically there is contraction and it becomes denser and denser. And that is why in one case we call it thermal expansion coefficient, where density becomes smaller if temperature increases, whereas in the other case, density becomes greater if concentration increases, right? And that's why in case B, we call it solute contraction coefficient. And both these equations that we have here uh, are quite useful, especially in this course when we are going to use these quite often, as most of our problems are related to uh, either heat transfer or mixing or pollutant transfer, where there is mixing or diffusion due to concentration gradient. And we try to relate that to this concentration to density so that we can calculate the buoyancy force, and that buoyancy force can be used to find the moment of fluid in general. Okay, so these are all the set of equations that we might be using in our course, where not necessarily all of them are conservation equations, but they are all very useful equations or fundamental equations that we may need.